Io parto, eh?
Okay. Yes. Guys, welcome to today's seminar, which is also our last seminar. Uh, it's a bit disappointing to see that we have only half of the usual um, attendees. Yeah, still, let's let's welcome Professor Nardi and his PhD students, Carlos and Mulam, who will talk today about um, robotics for precision agriculture and related topics. Daniele, thank you for accepting to present in these seminars, and also thanks Carlos and Mulam, and take it away.
Okay, thank you, Roberto, for the introduction. Let me say that I've been attending myself some of the seminars, and I think this year the seminar course was really uh, very rich, very interesting, and I hope you share with me this impression. And I also hope that this last seminar will attract some of your interest. Actually, the seminar is rather an overview of our research in a field that is growing substantially in the last years. The issue is robotics for agriculture in general, but in fact, the term precision agriculture is intended to address agriculture through the ability of acquiring very accurate information, knowledge about the crop status, and based on this information to take decisions that are um, much more specific or take into account the actual context to a very small level of detail. And why this is important? Well, on the one hand, there is, of course, as usual, optimizing production. But I think what is more important in this case is to, or in the case of precision agriculture, and specifically in our case, to reduce the use of pesticides and, generally speaking, to make the overall system more sustainable, avoiding to spread in the environment unnecessary amounts of pesticides, and at the same time make an appropriate use of resources. We are actually focusing on pesticides, but the other inputs for agriculture, like water, soil, nutrients, and all the other inputs that can be given to the field could be better regulated by um, um, detailed knowledge of the field. By the way, you may be thinking, some of you may be, that it is possible to do agriculture without pesticides, but this is actually not feasible, maybe not anymore, because we have experienced that some flower fields that we've been addressing in our research and we've been looking at in practice, without any treatment with the pesticides before the growth of the plants, you get to a point very soon where you cannot even distinguish the sunflowers plants in the vegetation, because all sorts of plants are growing, many of them growing much higher and much bigger than the sunflower plants, and therefore making the whole culture totally useless. So reducing is, I think, also a good target from a practical point of view. Okay, please make questions at any time, and I'll be happy to answer. Roberto will convey the questions to me, and I guess you have to use the chat for the questions. Okay, so how are we talking about precision agriculture today? We are going to first do an overview of the Flourish project. And in this part, we will specifically address the technical contributions that we have produced in Rome, and also provide an overview of the project. This Flourish project started in 2014 and ended in well, actually 2015, beginning of 2015, and ended in 2018. And there were a number of follow-ups about this after this project. And two current PhD students of mine will be presenting some of these follow-ups. In particular, Mulam and Carlos will do the presentation after the break. So the plan is that I will be speaking, excuse me, about 1 hour before the break, a little break, and then they are going to present their latest research, which comes after this project. Flourish is an EU project. EU projects are currently one of the most significant funding for our research. And in this particular project, the concept that was put forward, you have to understand that these projects are really research projects. So they are exploring ideas rather than providing complete solutions ready for the market. So it's quite exploratory research. From this point of view, you will see that the concept that Flourish is presenting, which is given by this picture, is quite ambitious, because it is based on the use of two robots, one small unmanned aerial vehicle, a drone, and a tractor that operates on the field. So the drone is much more agile, can fly, can get an overview of the field, and can provide information to the ground robot, the tractor, which is much slower, but on the other hand can carry the tools or the means to remove weeds. Actually, in this project, I will not go in detail. We've been trying 3 types of weed removal. Mechanical, and I think that the mechanical one, it's quite difficult and certainly not fast enough. And we've been trying also laser to burn the plants, but the laser power that is needed is significant, and the laser is a very thin, has a very thin ray, and therefore the system needs to have a very good and precise knowledge about the position of the stem, which needs to be burned. So actually laser also didn't turn out to be very successful. And therefore we are on the use of selective use of pesticides, which is also available already in agriculture fields, in agriculture practice, since the pesticides can be spread in the field through arrays of small sprays that can be controlled individually. And in this way, it is possible to do this selective spraying. So currently, I think this is the most effective way of handling the removal of weeds. So here is the concept, as I mentioned, quite ambitious concept. And here is the consortium. And together with us, we had ETH, Bonn University, French CNRS, and University of Freiburg, and Bosch. And actually, the robot that you saw in the drawing is a robot from Bosch. It's their first prototype that they have developed for autonomous robots in agriculture. We'll see a picture later on. And we had an agency from the Marche region, so we had the chance to go in the field because we had actually three environments where the practical activity was performed. One of these environments was at ETH, where they had a research institute with a very sophisticated setup for using sensors on a field based on the same type of technology that is used in order to film the football games in the United States. There is a big construction with these very high poles, and cameras are suspended through lines with a sophisticated system for moving them over the field without interfering with the game. So this is one of the sites. Another site was at the University of Freiburg, and the third site was in near Jesi, in Marche region. And there we proposed to address specifically sunflowers, while in the other settings, they were much more interested in sugar beets. Now, sugar beets are no longer produced in Italy because eventually they turned out to be not very cost effective. And therefore we focused on sunflower, which is very widespread, especially in the Marche region. But the key point is that we had a real experience on the field. And to me, this was a particularly challenging and particularly rewarding part of this research. Okay, so here is a timeline of the project. As I told, the project lasted a little bit more than 3 years. And it's challenging, the project, also because if you miss the right season, say, for example, because you plan to go on the field and that particular day is raining, if you go 1 week after, the crops have grown and maybe you don't find the conditions that you want to address in your study. So it's an additional factor of uncertainty in the overall project. Okay, here you should be able to see the final demo. And there are sugar beets on the field. It's very hard to see them. This is the view which is taken from the drone, but you see that there is another drone that is flying on the field. So the drone made an inspection on the field, and the robot is now moving and going to address the particular spot which was reported with the weeds by the drone inspecting the field. So we've actually managed to implement the concept that we had put forward in our proposal, even though, as I mentioned in the introduction, clearly this is not yet something that a farmer would buy for managing its own field. I have to say that between the two robots, the tractor is maybe the less attractive because it moves very slow. The reason why everything is moved at the high speed here is that the motion of the robot is still terribly slow. And one reason is that in order to detect precisely the weeds, the motion of the robot should be at a very low speed. Plus, controlling the navigation so that the robot does not step on the plants while moving is also rather challenging.
Sorry, Daniele, we have a question related to how
Yes.
how is handled the communication between the UAV and the tractor.
Yes, we will see later the details, but the UAV is we are able to exchange the map between the UAV and the UGV, and in fact, the map already contains contains information about the weeds, and the two visions can be realigned by a suitable algorithm. More specifically, we'll see that the map or the view of the UGV, the tractor, can be overimposed to the view of the UAV, and they can be successfully realigned. Okay, we'll go into more details about this later on. Okay, so here is how another video showing how the UAV is flying on the field, and you see the view after the processing, where the green represents the crop and the red dots, they're mostly dots, there are a few larger spots, they represent the weeds. Okay, so that on the right, you see the UAV flying on the field, and you see the map, and this is done online while the UAV is flying. So this information can be transferred to the communicated to the UGV. Actually, it is not a continuous flow, but typically the UAV is reconstructing, and then the point for the UGV is to match its own position in the map provided by the UAV. And here you now see also the image from the camera of the drone. You see in the little window on the left, which shows the image before the processing, and you see the result of the processing below. So this was actually quite challenging, and I think this is one of the first examples where the processing, for example, in this case, for crop weed classification, is done on board the UAV. And you see, probably you have been, or you may have heard that the use of UAVs is promoted by some of the companies that are selling nowadays services based on UAVs with sensors. But in that case, not only the flight is not autonomous, basically they would provide just the video of the recordings, and in few cases they will do some sort of post-processing offline. So the services that are provided are really not very sophisticated. Okay, let's move on, and let's see why I already anticipated that the UGV is a little slow. Let's see how it moves in the field here and what it can do and how it can do. Okay, So this is the robot is called the Bonnie Rob. As I said, it's a very nice robot because you see from the point of view of mobility, the robot has this interesting motion system where each wheel can rotate 360 degrees. So before, let me go back a little because I want to stop for a second on this image here. You see this gigantic black box that is positioned underneath the robot body, which is actually not so heavy, except that in this particular case, as you can see, it's fully covered with sensors of various kinds. Anyway, the black box is actually a protection from the light so that the robot can illuminate with artificial light the field and do the necessary image processing. So actually the detection of crop and weeds from the robot is quite challenging. And without such controlled conditions, the accuracy remains quite small. Okay, let's see now the video again. And see the motion of the robot. Here one example, it can rotate on the place. So now it's entering the field. And then you see now on the left upper part, the RGB image. So let's say the actual image, then the near infrared processing, which is used in order to say remove the background essentially. And there on the bottom you saw the result of the detection, and here you see the system with in this case it's only 8 nozzles that can be activated individually, and they didn't want to put color on the plants, so the water that is sprayed is not really visible, but in fact it's relatively accurate in catching the small plants. And you may wonder how these small plants can harm the culture. Well, first of all, at this stage, also the sugar beets are quite small, and in fact, the growing pace of the plants can be quite different. And as I mentioned earlier, without some sort of weed removal, the cultures will not be productive. Actually, go into trouble. Okay, here you see another view of this system with the nozzles to do and again you here see again the processing. On the left upper part, the RGB image, on the right side near infrared, and in the bottom part, the result of the processing. Okay, I think we can stop here and move on. This is, by the way, is in Italy, is in our location. Okay, this is, in fact, the highlights. We had this very nice demo with an interesting workshop, an interesting, it was an event with the local, farmers. It's actually maybe, it's a farm industry, I would say, because normally it's not just the individual farmer that runs a small business, but there may be much larger companies that do the farming overall. So here is the group. Here are some outcomes of this project. I enjoyed the project very much. I think it was very successful. And I have to mention that two of our students, like Ciro Potena and Marco Imperoli, that I mentioned in the initial slides, they got their PhD during this project. Okay, now let me focus on the contribution from our group. Okay, so essentially, yeah.
Yeah, we have a couple of questions, which are um, first of all, does the tractor get help from the UGV for the localization?
Uh, Not really. It's actually, well, yes and no, but I have to say that on the tractor, the localization is much more accurate than the localization on the aerial vehicle, because the tractor needs to be very accurate, especially it cannot rely. We will address also this issue. It cannot rely on GPS only. Even the most sophisticated GPS is not enough for proper navigation in the field. So the answer to the specific question is no. The tractor does not use the drone for localization. Go ahead with the other question.
We have two more questions. One is, it's a bit generic, which is, what is the type of processing used? I don't know what is specifically referring to, and maybe will be answered by later coming slides. But
Yes, typically, well, we started, this project started when there were still some image processing tasks that were addressed without neural networks, namely with more conventional, maybe learning methods, but not based on neural networks. Of course, towards the end of the project, we also introduced a neural network. So the main processing is done with the neural networks. But one point is that in order to apply supervised learning, you have to have annotated images. And having annotated images in this, having this annotation is quite challenging because we don't have, an army of people that can provide pixel-wise annotation of these images. I will show and I will discuss this aspect later. So be patient.
okay, we have one last question, which is the robot system still in use, or was it just used during the project period?
Well, that's maybe a good point. Actually, for reasons that I don't know in detail, Bosch had developed this robot through field. What's the name of the robotics? Field robotics, I think. I'm not sure about the name. So they created a spin-off company, but then they decided to say abandon this production, the production of this robot. So there are now other prototypes that can be used, but in fact also in other projects there are several mobile bases that are not autonomous. They can be controlled by a remote controller, for example, and that can be used in the field. In particular, there is one mobile base which is exactly like the Bunny Rob in terms of the setting of the wheels and the ability of the wheels to rotate and therefore have more agile movements, which is very, very good in the field. But the Bunny Rob itself has been dismissed from production. Any other question? Okay, so in this slide you see the Bunny Rob in the real thing, and this is the first part is a picture that we will see again later, and we'll show the one on the right, a very detailed study that we have done on the ground robot localization. The one icon or the one picture on the left right will refer to a study that we have done for the realignment between the UAV and the UGV points of view. And the third one on the bottom is a view of a synthetic field that we have built through a simulation environment, which was implemented in order to provide the data for the training of the classifiers for crop and weeds. So these are essentially the three contributions that I'm going to describe. And you see the two on the right are the two students, PhD students that I mentioned earlier. So I'm going to go in more detail in this three contribution. And here is the first one. The first one is what has to do with the crop and weed classification. But actually, instead of presenting a classifier, we will focus on the collection of data for the classifier, and in particular on the construction of the simulation environment, which I anticipated. Now, why the data collection is critical? Well, here we have an example of the interface that we had created. And through this interface, the user, and in some cases, it maybe require also some level of expertise and knowledge of the plants, it should provide a pixel-wise classification telling which pixels belong to a crop and which pixels belong to a weed and which are instead part of the background. And in fact, it's also worth considering the case of multiple classes of weeds, because different types of weeds may be treated with different pesticides. So again, in order to save and to use the minimal amount of pesticides, they should be focused on the type of weeds that are present in the field. Okay, so this is, we had, I think, 100 images annotated through this system. And then our domain experts came back to us and said, we are not going to do this because we have our own business and we cannot spend hours in front of a screen annotating the images for your neural networks. So here is what we came up with as a first attempt to address this issue. Here you see on the right the model of a weed. I don't remember actually the botanical name. And then you see a sugar beet plant on the bottom. And in fact, the reason why this may be a good approach, you can see from this little video, which shows that in software, you can create different configurations of the plant and therefore provide sufficient variety to train a classifier. So this is the variation on the crops, and up here we should have also the variation on the weeds. They have started at the same time. Okay, one stopped, that's okay. You see that you can, and this is all made by software. Okay, there is an algorithm which creates the plant and decides which types of leaves according to a random algorithm, deciding the orientation, the size, and so on and so forth. And well, actually, I have to say that this was, if not the first attempt, one of the first attempts to use this approach. And in order to make it work, we had to rely on a game engine which would provide a good rendering of these images. And here is the whole field. You can actually see that once you have the field, you can move through the field and you can actually fly the UAV through the field and gather images that can then be used in the classification. Or you can run your robot in the field and take the images. Actually, this type of simulation with the game engines is more focused to perception than to motion. In other words, there are usually not very sophisticated models of the robots. So for example, for maneuvers of the robots or things like this is not really the best simulation environment. But on the other end, it's very good for the perception. And it's difficult nowadays to find a simulation environment where both aspects, perception and motion, are dealt with at the same level of accuracy. Okay, so here you see again the results of the processing. And here you see the input image, and then you see the result of the segmentation and the comparison with the ground truth. Normally, these images are processed by using an index called NVDI. This index combines visual information with infrared information. So the infrared for distinguishing the green from the background is normally quite useful and improves the quality of the classification. And the net result, without going into the numbers and with the details, and maybe this aspect will be further developed in the presentation by Carlos, because he has been is our simulation expert at this time. It's important to point out that for our, let's say, our test case, we have been able to prove that we can obtain the similar accuracy even by combining the data from the real data and the simulated data, so that the real data turn out to be a small portion of the overall training set. And this, of course, would make the labeling of the data for supervised learning more feasible. Yes.
So the questions that we have are, first of all, which kind of information does the UGV provide?
I'll show later. It will provide a map with the annotation of the areas where there are widths, a sort of a crop width map of the field.
Okay. And the second question is, what kind of approach was used to, what kind of software, was used for producing random plants, and whether the approach was based on GANs?
Okay, this is anticipating the two topics that will be addressed essentially in the second part of this of the seminar. And Carlos will explain a little bit more detail. But in any case, the creation of the plants is a combination of the primitives that are allowed by these game engines, plus algorithms that create the plants according to a certain specification. So actually, being a computer scientist, growing trees for us is not particularly difficult, even though clearly the plants have their own structure that must be respected. Okay, other questions? Okay, then we move on to the second contribution from our group in this project, which is about the localization of the UGV. And actually, you think that localization is a solved problem, but in fact, if you have a field like this, and actually I think this is also a video that moves, you see that the features that a localization system may try to gather from the images on images of this kind would not be sufficient for a proper localization. Okay, so the images are quite uh, um, uniform, homogeneous, and there are no really distinguishable landmarks. And this is a problem for the localization. So in general, of course, you can use the GPS on the field, but the say the cheap GPS type, they are really not accurate enough. And the more precise GPS, the RTK, requires, first of all, it's expensive, then it requires a complex setting with the station. Maybe there will be improvement in the GPS technology in the next year, which will make this more usable. But at the same time, the GPS does not provide the heading of the robot, and therefore it needs to be combined with other sensors in order to have a proper localization. So we have conducted a study with the bunny robe, and by putting on the bunny robe really a number of sensors. And in particular, we have point cloud sensors, we have multispectral sensors, of course, we have cameras, of course, the robot has odometry. And in this setting, there are two types of GPS, the RTK GPS, which requires the base station that you see in the picture, and let's say a more and a cheaper GPS, which is less accurate than the other one. So with this setting, we have collected data sets, and then we have tried to study what is the benefit in introducing all these sensors in order to improve the localization. So maybe some of you are familiar with the model of a slum problem, which was developed by Professor Grisetti, among others, and the solver that Professor Grisetti implemented, the G2O solver for this graph optimization, where essentially a slum problem is modeled as a graph where each node is representing a position in the field, and each arc is representing the constraint that is obtained through a measurement that connects two different positions. And when you have multiple sensors, you can have multiple edges connecting two nodes, and you can run a single optimization process that can actually provide an estimate taking into account of the information that is provided by all the sensors, including sensors that are absolute, like the GPS, which can simply model into the mentioned framework as a loop, namely as an arc which is directed towards the node itself. So by combining all this information and creating this large optimization problem, we've been able to combine the information from all the sensors. However, in addition to the information on the sensors, we had three additional constraints that derive from a couple of assumptions that we make on the field. The first one is that the field is can be
Bambino,
dire
stasse, bambino.
Prima a disegnare che a scrivere. Cioè, il bambino subito disegna, immediatamente. È una cosa magica.
E tu ci sei rimasto?
In the field. And that there is a predefined field traversing route, which means that we are going to traverse the field according to the rows of the plants in the field itself. And this was translated into a number of additional constraints that you see listed here. Okay, here is one of these SLAM videos where you see in the end is a 3D reconstruction of the echicon. Actually, this data were collected in the ETH facility in a little city in Switzerland called Echicon. And actually the green that you see is the field, and this little tripod that you see in red and yellow, this is actually one of the structure that is holding the cables that allow to position the sensors, mainly cameras, on each specific location of the field. This is the one device that I was mentioning in the introduction. And as you see, I'm not really familiar with this 3D point representation, but this is actually quite consistent and makes all this SLAM passionate quite happy. Okay. So here is a numerical, there are some numbers. Actually, this work was all about improving these numbers. So let me give you some information that helps you reading this table that maybe you can look at in detail on the slides afterwards. In any case, first of all, on in the center part and in the rightmost part, we have the results based on the two data sets. So they are called data set A and data set B. Okay, these are the columns with the numbers. On the right, in the right part, we instead have for all the different types of sensors that could be added to the graph representation in order to obtain the position, then there is a check mark point. So, for example, if we take this row is actually the one before the last, is the one with all the sensors in it, okay? That they are, this is the visual odometry, this is the IMU, this is the Ackermann model, this is the elevation model, this is the information from the LiDAR, this is the Markov random field, which is introduced, which is another of the constraints, and this is the wheel odometry, the W, okay? So if you take this row, I think it's the second one, it's the GPS plus the wheel odometry. And it is the first, the cheap GPS, and in the second part of the table, we find the RTK GPS with the same type of structure. So the key point in this table is that you see this line where you find the numbers in bold, which shows that by adding all these sensors, there is a consistent improvement in the accuracy of the localization, where the ground truth in the data set is of course taken by a sufficiently precise external measurement system. Which is, I think it's a result in itself. And also we see that each of the sensors is eventually leading to some improvement in the final result. Okay, and of course the RTK performance are better, but still combining the RTK still gives to better precision. And in particular, even though this is maybe not so intuitive, the improvement of the information in the altitude the Z direction, led to a general improvement of all the other components of the position. Okay,
so we do have more questions on this part.
Ready.
So the first one is, why do we have to use the GPS sensor for localization? Instead of using it, we could use the fixed origin for localization, or maybe I didn't understand well the application of GPS in this case. This is the comment, I don't know.
Well, first of all, it's the first sensor that is used in all the tractors. And actually, it's it somehow seems an odd question, because it's getting the absolute position when you are fully accurate outdoor. It's just a gift, so we should really take it. Except that it doesn't give the information about the attitude of the robot, but that can be compensated by other sensors. So I think GPS is taken as a necessary basis for this localization. Anyways, other questions?
Yeah, another question is, should the map be rebuilt when the crop grows bigger?
Well, that's a good question. And it's to some extent it's a research question for people that are into SLAM. Mapping the same or navigating the same environment with very different conditions. Let's say plants that are grown, or maybe snow on the field, or maybe it is still quite challenging. So, of course, these results are limited to a specific picture taken. Other questions? Okay, so also these results are quite satisfactory. Here is also another type of interface, which is exciting for the SLAM experts, because here we see, I hope you can see, you see the robot moving. It's a white trajectory, and it's really going exactly on the ground truth, which is represented by the red lines. In any case, this interface is relevant because essentially it provides to work on the data sets that were provided by introducing or removing any of the sensors that were used in the acquisition phase. So it's a very rich data set, and the data set is available, the GUI is available, everything is available to play with and check actually the results. So final step that I have anticipated, or third contribution, is the realignment between the map reconstructed from the UAV and the view of the tractor. So maybe the tractor has a perfect precision in the positioning thanks to the system that I've just illustrated. But when the UGV transmits the map, how does this the robot realign its view on the map that is provided by the UAV? We'll see that we have solved this problem to some extent. Again, difficulties, I mean, similar problems have already been addressed in other scenarios, but here you have the same picture that I showed you before. And, if you have to find the correspondences that you see represented in the two pictures at the bottom of the slide, in this type of environment that you see on the top, you understand that this is really challenging. And in fact, state-of-the-art methods that are used for localization and similar things, they fail in realigning the two views. Okay, that you see, I think it's good to remark that on the bottom part, you see actually the two views. On the left, you have the UAV view, and on the right, you have the UGV view. And you see, in this case, you can do the association because you see the markers that have been put on the field. But on the other end, if you have to do this the association based on these two images, this can be challenging. Okay, so here, and of course, there is the GPS, okay? But in fact, if we take into account the GPS information, you see that there is a significant disalignment between the two maps. And moreover, the two measurements change over time. So you see that the blue, which is the perception, I mean, the view that is obtained just by taking the position through GPS, it doesn't really overlap with the red, which is the actual, the real match, is the ground truth. And plus, over time, this is continuously moving, and therefore it cannot be, this realignment cannot be done. And in particular, where the angle is mistaken, you see that nothing can be reconciled. And this is a critical step. And I think, after all, this is one of the most practical also results of our research in this project, because it's, this whole story, without this realignment between the UAV map view and the UGV view, the whole story, breaks, because there is no possibility to do the matching, and therefore to use the information taken from the aerial robot in order. Yes, you could do to some extent if the situation is, the field is highly inhomogeneous, but you cannot have really a precision matching in this case. Okay, so this is for the motivation. So how did we address the problem? Well, we addressed the problem by first turning the problem in 2D. So we take the aerial view, and we try to overimpose the projection on the ground of the view from the robot. And in particular, we consider the information about the vegetation and the information about the geometry, in particular the height of the plants. And actually, if you had noticed the previous slides, it's the rows of the plants have some interruptions, because maybe some plants don't grow well, and these interruptions to some extent provide a pattern, and it's actually based on this pattern that we can do the realignment in a robust way. So the height of the plants and the presence of the plants are the two key information for this sort of for our approach. Which is then developed by, once the 2D matrix with the information about the geometry and the information about the presence of green, the plants, is built. It's done using an algorithm that is borrowed from the computer vision, and it's called a large displacement optical flow. Which considers the realignment of images in optical flow when there is a large displacement. And plus, there is a refinement step which is done with another alignment technique for aligning two images and doing association, which is called, you should know better than I do, it's the iterative closest point algorithm. Okay, based on these two steps, we are able to do the realignment effectively. So here you see that in these two, from these 2 points of view, one of them is from, shows the RGB image, and you see that the views are correctly overlapping, and this is seen in 2D and from the 2D, but it's done, you can see the different views also in 3D. Okay, so this is working. Actually, also in this case, there is also a quantitative study. And the quantitative study is based on increasing the error in the initial guess and checking whether our approach is able to realign the two maps given an increasing error in the initial guess. The error in the initial guess can be a translational error or an error in the angle. And you see the two lines of graphs represent exactly the variation of these two errors with the other one fixed. And from the left to the right, there is an increase in the error. Okay, so the farther to the right, the more is the error. And in fact, you see that in the rightmost graph where the error is 30%, the system starts to misbehave. So in the end, we can state that we can get the proper realignment with an error about 30% in the scale and 5 meters and 0.2 radians in the initial guess. So everything is again open source. And as I said, this is, I think, a tool that can really be made practical in the cases where one needs to combine UGV, aerial view with the ground view. Okay, with this,
we have a question on this, which is what kind of data association did you use in order to perform ICP?
I don't understand the question. The data association in this case is to properly associate the points in one image with the points on the other image.
Yeah, I think the question is if the data association was done using only the point information or also line information or this kind of thing.
I think it was a pointwise data association.
And only geometric information or also
as I said, it was the information about the green. Okay. So we have two matrices. In one matrix, there is in each element of the matrix there is information about the presence of plants and information about the height of the plants. So geometrical information and information about the presence of plants.
Okay.
And with two matrices of this kind, we do the association. Okay, so now I'm here. Flourish is finished, and here is the follow-up work. I will speak about how long. I don't have the clock here. Let's see. So maybe I should stop quickly. Okay, so I can speak briefly about one specific case where we were able to provide maps that can tell the presence of downy mildew, which is in Italian peronospora, and this is for the sunflower. And then we will hear from Mulan, maybe after a little break. about the recent work on crop weed classification and the use of GANs in particular, which was anticipated by some of the questions during the presentation. And then we will see the developments that we have done on the simulation environment, where there has been a change. We moved to a different software environment, which is Unity. But more important, we have been able to model in the simulator also the information related to the use of infrared, the infrared band. And this is particularly interesting for the case of plants. And we see that we will see that this also improves the overall training done with the simulation, with the simulator. Okay, let's talk briefly about downy mildew. Okay, here is the situation. The plants that are affected, this is a sunflower field, and the plants that are affected by this pathology are suffer from or exhibit several type of symptoms. They are related to the color. They tend to be much more yellowish than the normal plants, but more than this, or maybe more interesting for our purposes of detecting the infected plants, the plants suffer from dwarfism. They are actually much smaller, much, yes, their height is low compared to the regular plants. You can see this in the real field on the left, where the plants in the foreground are much smaller than the plants in the background. Why this is important? This is important especially on those fields where they cultivate the sunflower in order to have the seeds for the next season. Okay, so in this particular case, they want to make sure that there are no sick plants, because otherwise the disease will spread in the following season. So in practice, the people have to go in the field, and inspectors actually, and they have to prescribe to the farmer which plants they have to be removed. So I think that the people that are working for the public institutions that have to take care of this, they would be much happier if they could fly a drone and come up with a map which is telling directly where the farmer should go in order to remove the sick plants from the field. So we wanted to, in this work, to detect infected plants. Of course, we are using a machine learning solution, and we also want to exploit to some extent also the synthetic image, or the use of the simulator. Okay, let me start speaking about the simulator. In this particular case, the images of the plants are not so important. What is more important is their structure, because we simulate in the field the presence of plants that are affected by dwarfism, and therefore they exhibit the symptoms of this disease, which are the color of the leaves and the height of the plant, essentially. And we have been experienced ourselves that going in the field and flying a drone, going back home with a video and reconstruct from this video a good 3D representation of the field is usually not successful in the first attempt, because maybe you flew the drone too high, or maybe you flew the drone too fast. So there are a number of parameters and adjustments that need to be taken in order to enable the softwares for reconstruction, like photoscan that we are using, but this is just one of that is available on the market to do a proper job. So what we really used the simulation for in this case was really to simulate the flights of the UAV on the field at different heights, at different speeds, in different conditions, and then provide the images to the software so that the software could effectively do the reconstruction. In this way, we were able to go to the field, which in our case, by the way, required to take the train, go to for 2.5 hours, then go by car to the field, and then do the run with the UAV. If this was not successful, it was some sort of a problem. And so being able to do these trials in simulation was particularly time-saving and effective for us. So once we have the images taken from the field, we do the 3D reconstruction. As I already mentioned that we do this with conventional software. And then we do a number of steps in order to obtain, in the end, a map which highlights the presence of sick plants by classifying them, by distinguishing them from the plants that have no disease. So the first step is soil and crop separation. And this is done through a dedicated machine learning step. This is relatively straightforward and can be also based quite effectively on the use of infrared. And then we had to do some sort of realignment, because even with the small variations in the altitude, this is a little slope in the field would completely screw the measurements of the height of the plants, and therefore we had to realign all the plants in a flat plane. And then once we have this realignment, then we do some height normalization, and then we have a classification and classifier which can distinguish the infected samples from the non-infected ones. Okay, so I'm not going into the detail of the classification. Juan Pablo decided that we better use the SVM because we have a small amount of data overall, and for the 3D point cloud, SVM seems to provide good results. There may be better approaches, but what is important to us is that, well, crop, soil, crop or soil plant classification is relatively straightforward. But in fact, what is nice in this work is that we obtained quite good results in the mapping of the plants in the fields. And this was these good results were achieved also in different weather conditions. The 4 data sets that you see represented here are cloud morning, cloudy afternoon, and clear morning and clear afternoon. So we had data from these different bunches to test our overall approach. And the accuracy is certainly quite suitable for the particular application and quite interesting in general. Okay, let me summarize and close. Well, with this particular work, we have seen another application of simulation environments. More about this after the break. And then we have seen that the mapping problems that arise in this agriculture scenario with the tractor and the UAV and the realignment of the positioning of the, especially of the UGV, and the realignment of the two can be suitably addressed. And we found interesting solutions. Okay, I'm happy to take more questions, and then I let Roberto decide about the break.
So there are no questions at the moment. So let's take a 10 minutes break and then we'll restart. Okay?
Okay.
So I will stop your sharing, I think. Can I?
I can stop the sharing myself.
Okay, yeah. Okay, then see you in 10 minutes. We'll stay connected, of course. The streaming will stay on and we'll be back in 10 minutes.
Of course. I will be around after the break. Also, if there is any additional question, I'll be happy to answer.
Okay, thank you.
So I will start now. Okay, I'll share my. Okay. Hello, everybody. I'm Mulham Fouakharji, PhD student in engineering in computer science under supervision of Professor Nardi. I will present you my recent research area. It's multispectral image synthetic for crop width segmentation and precision farming using GANs. So as a Professor Nardi give you a good introduction in precision agriculture, I will move directly to introduce the GANs and generative models. So generative adversarial networks are an existing recent innovation in machine learning. It's an machine learning models can use the instance that resemble our training data. Examples, GANs can create images that like photographs of human faces, as we can see in this slide. These human faces are not real. It's generated by GANs in this paper published by NVIDIA in 2018. So what is generative model in general? In general, it's like we know in machine learning, we have known, I guess, discriminative between two classes. This is called discriminative model. The network here have the ability to learn and distinguish between two kind of data, like distinguish between kind of animals, I don't know, kind of different objects in the classes. Here, the generator tries to generate and create new images that's like real enough for us, like new images of animals or cat or dogs or any kind of data. So, sorry. Let's describe the GAN structure. Any machine learning models have the simplest structure, which is like we have input and the model and the output. The input here, we have random noise and the model is generator, and the output should be like a kind of images we would like to generate, like a human face or any kind of object. And but we need to know how much is through this object we have. So to do this, we have another model which combined to the generator model called discriminator. So the main parts of GANs, it's two. The first one is generators, learn to generate plausible data, and generate instance should be negative training example for the discriminator, and this will explain better after in the coming slides. And the discriminators should learn how to distinguish the image generated by the generator, which is considered fake data. And we have another resource for the discriminator to make him learn the difference between the real and the fake. So we have another source of input for the discriminator. It's a real data, which we want to generate. So as training process begin, the generator start to produce, obviously, as we can see in this shape, like fake images. And this generator can easily distinguish fake and real. And as training progress, the generator gets closer to producing and real images that can be fooled the discriminator. And finally, if the generator training goes well, the discriminator gets worse at telling the difference between real and fake data. So it starts to classify fake data as real, and its accuracy decreases. So going deeper in this structure, discriminator in GAN is simply a classifier, like any kind of a classifier could be used artificial neural network. This should be appropriate to type of our data we want to classify. Here, when we're training the discriminator, we have two resources of data. The one of real data, symbols from real data, and the one should be these real images, such as picture of people, if we want our GAN to generate people faces, or in my research, like crops and weeds. And discriminator uses this instance as positive example during training. And the other input is like fake data, and this is created by the generator. The discriminator uses this instance generated by discriminator as negative training examples. So how is the training of discriminator goes? When we start the training, the loss function of the generator try to make the discriminator well distinguish between real and fake data. So when the training goes with the discriminator, we start training the discriminator between fake and real data. We freeze the generator because we want the generator just to create the samples in this area. So the loss function of the discriminator penalizes the discriminator for misclassifying a real instance as fake or fake instance as real. And then we start to propagate the weights by backpropagation from discriminator nodes through discriminator network. For generator, the generator, as we said before, it learns to create a new data instance considered fake data, and it's try to make the discriminator classified as real. So training here requires tighter integration between generator and discriminator than the training process of the discriminator by itself. And here the generator loss penalizes the generator for failing to fool the discriminator of predicting his generator samples as real data. Here we can see like we use for generator input random input because in our research, like or here for our model objective, we don't need to use input for any kind of usable data. I mean, we don't need to distinguish any two types of objects or anything. Just we need the random noise that we can start from it to generate a new object, and this noise should we can get the produce wide variety of data and sampling from different places in the target distribution. So we can see like generator is not directly connected to the loss of the discriminator. So we are trying to affect on the loss that is not connected to, and this is considered like area of research, and it's a hard area to do. So generator loss try to penalize the generator for producing symbol that discriminator try to classify it as fake. This extra chunk we can see, I don't know if we can see the slides now, include the backpropagation from generator loss and modify the weights of the generator by calculating the weights impact on the input. At the same time, we don't want the discriminator to change during generator training, because if we did so, we are trying to hit a moving target, and this makes the problem more hard for generator. So describe as fast the training problem here. We start from random symbols, and generator produce output of from random noise, and then the discriminator try to classify these symbols real or fake, and we calculate the loss of the generator while training the generator, and then we do backpropagation based on the gradient of the generator and modify the generator weight. And this is considered like one iteration of generator training. So now let's see some kind of application of GANs. Like the first application was in this paper. They try to generate a new plausible example of MNIST handwritten digits and say for small object photograph dataset and Toronto face dataset. All these objects like generated using GANs, and the GANs here built with multi-layer perceptron, and you can notice like these images like generated with low quality. So the next work, they try to make the GANs more effective by introducing a new structure of the GAN, which is called deep convolutional generative adversarial networks, DCGAN. And this have certain architecture and constraint and demonstrate that they're strong candidate for unsupervised learning. And we can see here like they try to In this paper, they try to replace all pooling layers with the strided convolutional and all fully connected hidden layers with deeper architecture to make the training process easily and faster. In this paper by NVIDIA, they show the power of GAN of generating new resolution and new high resolution images that describe new training methodology for generative adversarial network. The key idea here is growing the generator and the discriminator progressively, starting from low resolution and then adding new layers to the model increasingly, which details as training progress. This both speeds the training up and greatly stabilize the training, and this allowed to produce high quality image. As we can see, all these images is like generated by GANs, and it's not there is no real faces like this in real life. Another application used to augmentation task. In this paper, they try to generate realistically looking high resolution images for skin lesions with GAN. They use small training datasets up to 2,000 samples, and the natural data allows to done direct comparison between the image statistic of the generated samples and real datasets. And in agriculture area, this work contribute by providing a method for optimizing realism in synthetic training data generated by gaming engine. Like they improved the state-of-the-art machine learning method that semantically segment the plant parts. Their hypothesis that the similarity between the synthetic and the empirical images can be reduced by using adversarial generative network by doing image-to-image transformation. We can see here from the image we have like synthetic data and empirical data, and try to use the GAN. Actually, here they use kind of GAN called cycle GAN, which used to image transformation. So they try to move the image features, color features from the synthetic view to empirical view using the GAN. So going back to our problem here, we're trying to, our objective here to minimize the environment impact by reducing the reliance of chemical productions such as herbicides and pesticides. So we are trying to do like selective spraying tasks on the weed in the field, and this is considered hard and hard task for the human and time consuming. We can see like we have variety type of crop and weeds. We have different light of conditions in the area. So farming robot can play important role in this mission, since they can carry out precision weed control by selective treatment applications. And the fundamental requirement to perform these selective treatments, we have to build effective perception module and should be capable to identify and localizing crop and weed in the field, and those to trigger the proper weeding actions. The commonly adopted approaches use the vision approach to tackle this problem. So it relies on machine learning method for computer vision, such as convolutional neural network. The problem here, like we have these data-driven methods that allow to train powerful visual classifier that report the high classification performance. It's strongly depending on the size and variety of training dataset. Like if we want our classifier working in different lighting condition and different kind of crops, we need different data and training phase. And this problem is well known and addressed in different and many ways. So the more recent approach address this problem is diverging on generative adversarial networks, as explained before. So they try to augment the dataset using GANs. So in our work, we propose an open methodology to sanitize photorealistic images by using generative adversarial network. And unlike to usually convolutional use of GANs, we aim to train a model to generate an entire cell. We generate the semi-artificial images by replacing with synthesized photorealistic counterparts only the same object that belong to the object classes that are relevant to target perception tasks. So, and some few words, like we are trying now to not synthesize the whole scene. The whole scene include like a crop and weed and soil. we try just to sanitize the crop and wheat, which is like our target of learning in this area. And the main intuition of this idea, like usually, vision-based learning classifiers are not able to equally generalize across the target classes. Like if we look at the crop weed classification, we can notice like for soil segmentation, we have high performance, like nearest to 99%. But for crop and weed, we have lowest accuracy. So this aim to turn lead to unbalanced classification performance. Given that the proposed method exploit again to only learn the data distribution associated to subset of the target classes. So we need to learn the subset of target class, which is here in our situation, the crop and wheat. And this allowing us to train more compact generative model and to create photorealistic training sample in the faster and more effective way. So to achieve our goal, we use a conditional GAN, where the generative model is trained by conditioning the shape of the generated object. We can see in this image, like we have two input for the generator. Like a normal generator, we have one input, which is noisy or random distribution. But here we have another input, which is Y, which reflects the mask of the crop or weed, which we want to generate. And this helps us constraint for the object shape extracted from real objects. And here the generator will sanitize new realistic objective while keeping their original footprint on the image static. So our generative architecture will also take into account near infrared information. So we consider 4-channel input. We have RGB. Besides to near infrared, we have multispectral synthetic images. We use in this step like kind of GAN called spatial adaptive denormalized spade architecture, which is a typical conditional GAN. And differently from other common C conditional GANs, this network can perform a semantic image synthetic by converting a semantic segmentation mask into photorealistic images. In other words, the input-output behavior of this spade is opposite of the image semantic segmentation network. Like in semantic segmentation, we have the input real images and the output the mask. Here we have the opposite. We have the mask as input with random noise, and we have the output is the real images. So evaluation of the GAN is very challenging task, and several aspects need to be taken account and considered while defining matrices that can produce meaningful scores. These matrices should be capable to distinguish between generated and real symbols to detect overfitting. Our goal here is to check whether learning generative model will generalize with respect to problem photorealistic crop generation. Like our models can generate well examples or well samples that is close enough to real data. So for most GAN presented in the literature, they based on the manual inception to check validity of the generator symbol. And this evaluation is still considered the best approach. But this considered time consuming and sometimes it's subjective and often it can be also misleading. In our work, we employ an empirical evaluation. The basic idea is to use the symbols generated by the network and symbols collected from real data. So we have for the evaluation two kind of resources of information, one from real data and the other one from the data generated from the GAN. Then we calculate the performance after extract features from each one of these symbols. So extract features from the real symbols and the symbols generated by GAN. And we use 6 matrices to compute this the evaluation of this of our method. So we have 6 matrices, including inception score, mod score, kernel MMD, and Western distance, and inception distance, and first nearest neighbor. And most of these matrices is carried of measure the distance between two distribution of data. So we know we need to know if the samples generated by our generator is like coming from distribution close enough to the real distribution of real data. So we can see here that training steps from starting from the mask and noise and growing with the real images and this 300 epochs of the training phase. This for RGB data and this for NIR images. We can see like the resolution is getting improved by increasing the epochs in the training. So after generating these symbols, we need to create the full scene to use it in our purpose for crop width segmentation. So the final step in our approach concerning using crop and width RGB and NIR images to create the realistic agriculture scene. And to do so, we follow the following pipeline you can see in the slide. First, we get the crop and width mask from full mask images. Then we use this mask and resize it as input for SPADE. The SPADE network then generates a random photorealistic crop width instance by using shape of the input mask and random noise signal. The generated images is then replaced into the source image. So to do more evaluation for our method, we use the data generated by GAN to train a semantic segmentation network. So a quantitative evaluation has been carried out to show that by augmenting training dataset dataset of state-of-the-art semantic segmentation network with synthetic photorealistic images generated by our models will improve the network generalization capability and increase the performance of crop width segmentation. Moreover, we have no annotations effort here because when we use the CGAN, it generates both images and the mask. So to test our method, we use two open source data sets, both of them for sugar beet. The first one coming from Bonn, the second one coming from the Stuttgart. And both of them collected by using push pony robot, farm robot, moving on sugar beet field across different weeks. The dataset are composed of imaging by 4 channels, RGB and NIR camera mounted on the robot and facing down ground. We created 4 dataset to serve in our experiments. The first one is original, which is reduced version of the Bond dataset. We took totally of 1,600 images, and we randomly choosing among different days of acquisition in order to contain different growing stage of the targeted crop. Then we supplied it into training set 1,000 images and validation set the 300 images and test set 300 images. The second data set we mentioned as synthetic crop, which composed of 1,000 images with synthetic crop generated by using our architecture. The other data set with synthetic wheat composed also with 1,000 images with synthetic wheat generated by using our architecture. And the last data set mentioned as mixed, containing 2,000 images composed by union of 1,000 of original data set and 1,000 images with synthetic crop and wheat. For testing, we use the 300 images from Stuttgart and 300 images from Bonn dataset. And we use the Stuttgart dataset here to show the improvement in generalization capability of semantic segmentation after augmenting the training set with our approach. I need to point out, like here, we replaced with synthetic generated plants only plants whose stem is totally farmed into the image, because most of the farm and original one is kept. Like when we have the plant stem is out of the frame of the image, we discard the replacing with the synthetic one and we keep original one. So we use for dataset described above to train 4 state-of-the-art semantic segmentation network, namely like we use UNet ResNet, which is like UNet with ResNet 15 backend, and PonNet and SigNet. And to evaluate semantic segmentation output, we use the following matrices, which is per class intersection over union, average class intersection over union, and per class recall and per class precision. So we can see here in this table, like quantitative result of semantic segmentation on real images held out from bone dataset. And we can notice like for all architecture, the results show that intersection of reunion increased by using original dataset augmented with synthetic one. And this compared to only original dataset. And moreover, using only the synthetic dataset also leads to competitive performance when compared using only the original one. And in some cases, like when use unit RESTnet architecture, and we use only the synthetic dataset, our results overcome the results coming obtained by using only the original one. The another experiments done, we need to show here the effectiveness of NIR generated index. So to show the improvement in generalization capability, we also used here Stuttgart dataset as test set. And for all test architecture, the generalization capability improved when using a mixed dataset, which contained dataset coming from real and synthetic one. And also here, like we can demonstrate, like in this case, like when we use RGB plus NIR images in the experiment, we have like more accuracy, and this support our claim that we have like a good synthetic NIR index generated by GANs. So as conclusion, we introduce a data augmentation strategies that reverse on conditional GAN to generate entire agriculture scene by synthesizing only the most relevant object for semantic segmentation purpose. The core of this proposed approach consists of exploiting the shape of real object to condition the training GANs models. The existing shape are extracted from real-world labeled images. In addition, the generated process also sanitizes the near-infrared channel. And the obtained synthetically augmented dataset can then be used to train semantic segmentation network. We applied this method here for crop width semantic segmentation, and this well-known problem in agriculture robotics, and show that like a CGAN augmented dataset can improve the performance of different semantic segmentation architecture for this task. As future work, maybe we can use this architecture to generate the 3D crop suite images can be used later in the game engines, and also we can implement it in different research area. Thank you. Question?
So at the moment there are no questions. So maybe some will come, and we can answer them before. I mean, after Carlos' presentation, before we close.
Okay.
So thank you, and I guess it's Carlos' turn. Carlos, are you there? I guess he crashed. Daniel, should I go on Zoom? Sorry.
He's saying, can you hear me? So it's online on the chat.
No, we cannot hear you.
But we cannot hear. Which is worsening the situation because we could hear him before.
Yeah, I don't know. Did you join the audio, Carl? You're muted now. I don't know. So I don't know if you joined the audio. Okay, so let's yeah, if you have the Meet open, that is not going to work. So guys, I'm muting the sound for a few minutes until we solve this, and when it's working, I'll return it on. Okay, so we're back, and Carlos, you can take it away. Thank you.
Okay, hello guys. Sorry for the interruption. My name is Carlos Carbone. I am going to show you a presentation about simulated perception in video game engines for precision agriculture. And first of all, I want to thank you all for bear until this late in the day. I know that many of you are tired right now. So bear with me, and I will try to make this presentation as joyful and as less tedious as possible. And first of all, for you to guys know who I am basically, my name is Carlos Carbone. I am a second year of the PhD. I was born in Panama, but also Italian, and kind of an interesting fact. And my interests are robots and video games. So all of that converged in me working for simulations in this PhD. So then, what are we going to be seeing today? Basically, I want to show you, talk about a little bit about game engines. What are the challenges we have faced in managing these game engines, and what are the cool experiments we have been able to get out of these tools that we have developed. So basically, the first question that we need to ask ourselves is, which game engine do we want to use? Well, first of all, a video game engine is a software and that allows us to create games. As the word suggested, basically they are mainly created to create video games. Therefore, they are highly optimized to show you beautiful images with that can be rendered in real time. So that was highly of our interest, so we can do the simulations. I have a decent visual, so we can do all of our deep learning machine learning trainings. So, well, the first question is precisely what we're going to use, and the two most famous ones right now are Unity and Unreal Engine. So, well, I spent the first months of my PhD trying to figure out which one we were going to use, because we were already working on Unreal Engine. By the way, I'm a Unreal Engine super fan here, so I was trying to fight really hard for us to stay on Unreal. But in the end, it came down to we needed as much compatibility as possible, because we had many students that were interested in doing many things with ROS and some other complex algorithm things, and we needed to make sure that whatever we created with our simulator was compatible with those things. And unfortunately, Unreal is not very friendly with Linux, and we needed to have Linux as our main operating system, since we're using a lot of the robotic operating system. I'm still showing this because I want you guys to know where we are, suddenly changing from one to the other, because Unreal, in my opinion, has better realistic illumination, but we need to be practical. And we're still debating every now and then, or if every now and then we want to do some experiments with Unreal. For some reasons, I'm gonna talk further on. But at the end, everything that I'm going to be talking today is going to be about Unity. So now, having Unity, precisely this is one of the things that we needed to have it as compatible as possible with ROS, because most of the experiments in the past has been by the students have been developed using ROS. So we need to make sure that our simulations are compatible with those. Then what were the challenges in bringing the coming from Unreal to Unity, so you can get an idea of what is our work environment, my work environment to be more precise. But some from time to time, some people work with me. Basically, the main challenges are, okay, what are the things that we need? We need the models, the textures for the plants, because everything that we're doing is for precision agriculture, and then we need the realistic shaders. I'm putting that in red because that was quite a headache. And then we need to be able to create the procedural fields and the robots and put in UAV, because that was our first approach, using area vehicles inside the simulator. So I think somebody asked, like, how we doing the models, the actual plants. Well, basically we always start from the actual leaves. And well, this is basically a plane, and you can see the blue square is basically by the way, just for me to have know what I'm doing, can you see my mouse? Do you know where my mouse is on the screen, Roberto?
Yes, we do. It's very small, but we see it.
Okay. Well, basically, because I want to highlight that, okay, this square blue right here, I just removed the leaf just to show, like, okay, this is how the 3D model looks like. It's literally just a plane, and in the beginning it has nothing, and then we use through this really bothersome realistic shaders, we make it look like this. And I am saying bothersome because there's some things that you wouldn't expect that they were an issue, but unfortunately they were an issue in Unity. Like, for example, I need the leaf to be visible from both sides. I need to have a realistic visuals from both sides. I need that the cuts, the holes in the plants are realistic, and all those things were not saved by default in Unity, so we needed to develop them. But then once we have them, we have the actual plant, and well, like I say, I have these black lines that probably you cannot see them because they're really small. Basically, I am showing here for demonstration purposes, but in the actual simulation they are gone, and you can only see a leaf, and that's actually what we need. And I'm gonna try to make sure that that makes sense in a little bit. Then the thing is that, well, then we bend the leaves manually, actually, because technical reasons. But in the end, we do a couple of bendings of the leaves. So basically, you have, like, let's say like 8 versions of the leaf in different bending positions and different sizes, and then we play with those to do and what I'm calling here procedural fields, because then we to actually create the field, we multiply this to actually create the gigantic field. So where does that take us to the experiments? So basically, I'm going to be showcasing here 3 experiments, 2 by previous students and 1 that is my latest addition. And I have participated in all of them to a certain degree. The last one is all me. And basically, the first one is here. This was the first thing that I was doing on my first year as a PhD. I was helping this guy trying to create this field of sunflowers, and I made the code to make it as procedural as possible, as random as possible. As you can see, well, at least in this particular image, it doesn't make that much sense with real life because they should be pointing in one direction of the sun because there are some flowers. But I wanted to give the student as much flexibility as possible. So yeah, as you can see, there are the sunflowers that they have different sizes, different positions, all extremely random. Basically we have the sunflowers, the wheat, and then a little simulated drone, and then there's a fly path over it, and it takes the image just like it will be in real life. So because basically the idea of this whole thing is, we like to stay on our computers and not go to the actual field and be burned by the by the sun. So we try to see how much of that time we can save doing these simulations on the lab, and save time and energy and sunburns. So then the next experiment, these images are of my experiment, the ones on the left, but I'm showing here to you because I think that this is the latest update of the engine for this particular plant, the sugar beet. The idea here is that I wanted to take the simulation of the sugar beet a little bit further, and I'm gonna explain that later. But here right now, my point is, okay, this is what we had before on Unreal Engine, just to say like, yeah, Unreal Engine is super beautiful and everything, but we can also have a decent visuals in the Unity engine as well. And on to the right, we have the Unreal Engine. On the left column, we have the real images. We had on the right column, the simulated ones, so you can see they're pretty similar. And in Unity, we're doing the same thing. I have real images and I have images simulated to the right. And we also managed to achieve really nice, realistic imagery for our deep neural trainings. So then the first experiment that an old master student did is that he wanted to create a convolutional neural network to be able to have it compatible with swarm of UAVs, and that's actually one of my favorite topics. I am trying to work in that direction. Basically, you have a swarm of UAVs, and you want them to be able to share, like, okay, I saw these plants here and we want to go that way, and they start recognizing them so they can do better strategies on field coverage. But the thing with deep neural networks is, as you can see, it takes an extremely high computational power that you cannot put in a UAV, or at least it will be limited. So the idea of this deep neural network was to develop in a way that part of the input was the output all as well of the neural network. So what do I mean? Basically, the idea is like, okay, I have one take of the images. First, I have no output because I haven't, this is my first try. And then I say like, okay, I found that here are some plants and here are some weeds. And then the next thing, and then I try to re-scan the area, and I do the input again, but I also do I also put the output of my first attempt. So then the idea is that the outcome is going to improve. And the beautiful thing about this is that the load of analyzing and visualizing the plans can be shared among the UAVs. And hopefully we can manage in the near future to do really cool things with that. And the results are also sound. They did 2 data sets, and basically they were playing excuse me, and they were playing in the training, because of that. Another thing that was a challenge in the training was like, okay, how many of these images, and during the training before we haven't put the UAVs yet out there, like how many of the images I'm going to also equip them with an actual output, because at the beginning I only have the images, even if they're simulated or real, I only have images, and I need outputs for the neural network to be trained properly. So basically they were playing, the guy was playing with, okay, like 25%, 50%, 75% of the data set is going to be equipped with an actual output to see how it plays along. In all of the cases, it was clear that the performance of the neural network, the accuracy, the precision, it will increase as you were getting more views. Basically, all these tables are showing like, okay, observation sequence, like, okay, this is my first attempt, my second attempt, my third attempt, and you can see how I'm managing to get a higher value. All these scores that are going elevated, here's going up, here's going up, here's going up. The only exception, just to make the point that, also when you're doing deep neural net classification segmentation, we also have the issue that sometimes your data can also confuse the neural network. So I have had experience with trainings in the past that if the data is not that good, or let's say, let's put it a little bit more in an objective context, like if it's not compatible with the scenario of the real images, like if let's put a real quick example, like I do, all my data set is with a really sunny day, like super clear, and my images are super dark. Sometimes that confuses a little bit that kind of things can confuse the neural network when it's like, okay, I wasn't trained to scan plants in the dark. I was trained to scan plants in the sunlight, or vice versa. So then you need to be careful with that. And my point with that is that sometimes you can have these kind of results, but that doesn't mean that the results were necessarily bad. You can prove your point, like, yeah, this is actually working, but this particular scenario when you need to watch out. Then because my experiment, the experiment that I was working on is the near infrared sensor. This was quite a challenging thing because the main problem is it's not a problem with the game engines because they are designed for games, and we are not actually doing games here. We're just taking advantage of what they are. But the fact that they are games is that their whole purpose is to make gamers say like, okay, this is beautiful, I want to play this game. And that works on making the human eye think this is pretty. So therefore, the issue is that I can only simulate actual lighting that the human can see. And the near infrared is a bandwidth that we humans cannot see. So I needed to find, I don't know, an ingenious way to introduce this sensor and this engine when it wasn't modeled, to put it in some sort. So I needed to find like, or I need to become physics person and figure this out, or I could do this other particular process we did that we actually went out to the field and they took the pictures and make sure that the pictures went as plain as possible with the near infrared sensor images, textures, and we departed from that. So basically, what do we need? We need the synchronized textures. Basically, is okay, I have this plant and I need to take a photo of it with the RGB information and with the near reference information, and I need to make sure that they match exactly. And then I brought that to the engine to generate the data set to something or not training. So because the whole objective here is like, okay, I want to try to make sure that I can create I can train a deep neural network without trying to see if I can beat using real images, using synthetic images. And that's the whole purpose of all the simulations that we have shown you in this afternoon. So for my experiment, I needed these textures. I needed a real data set to compare, a convolutional neural network that was specialized for these kind of things, for plants, and then our famous and super awesome simulator. So basically the idea was that, okay, I needed what I did is that I used a camera to actually take the photos of these plants that I am mentioning. And I took and the weeds in particular, because the plants were in a place that was all nice and perfect, so there were no weeds. I got the weeds from another data set, and we put them in the simulator. We generated the data set, and we busted here in this convolutional neural network and see what happens. And we have really nice results. So basically, how did it went? Like how was my part of my work day as a researcher in this whole experiment work? Well, I went in the middle of July in the burning sun of the midday to take these images that you see here, and I took a piece of board, a whiteboard, to take the pictures of the plants and have them as isolated as possible with this camera. Sorry, with this sensor over here. And so then when I was on the computer, I was able to crop them in Photoshop. Well, I didn't use Photoshop, but you get the idea. And basically, when I got the images, the actual plans cropped, I was able to have them as isolated as possible. Actually, the image that I showed a while ago of sorry, the square that I am showing the leaf isolated, the texture that was used there was one of these. And so now I have the RGB images, the near infrared images of the other plants, and I stick them on the models that we had, and I was able to create. Oh well, and I also did the same thing for the widths. So, but the images I didn't take them myself. I got them from a real data set, and I was able to extract the widths by using the mask information. I wrote a program that went through all of the images and extracted the actual width information. And then I created my fields with the procedural script that I told you about. Like the sunflowers, I did the same thing, but with these images. And then I started to take, sorry for the jump. I think I missed one image here. Sorry, I am missing one image. Sorry that I am jumping. I need to go back. Exactly. Sorry, I needed to add this image again in the front, but I forgot it. Basically, this image here is exactly what I took. What I showed you earlier was the field in general, but the actual images that I started taking and taking and taking to generate the database, they all look like this one right here. And this is the RGB, and this is the near infrared sensor. So then I built my data set, and I was ready to put all of this um, in the bondnet network. So I had the convolutional neural network that had like really good results, and I was highly available. Like it was ready for everybody to use. And like, not all neural networks are, nicely posted on the internet for you to use. This one was, so this one that I took, and fortunately it was also tested for this kind of segmentation, because just for the people who might be still at this point a little bit confused about what's the point of all of this, is that we want the computer to identify, okay, this is a weed and this is a good plant. So the idea is that now that I had all of these masks and generated, I had my data set with my real data set, the one I can show you the link if you want. It was the same one that I used for to get the width. I got my data set from Unity, and then we also have the nice idea of mixing it with have a mixture of both, and we put them in the bondnet network, and we then compare it to a different another subset of the real images, and 820 level images with this resolution. So we basically compare all these trainings to these images on the side, and here we have the results. And basically I was using, to measure how good I was doing, I used the intersection or union method, and this proves that yeah, obviously the real one is going to have a higher performance, but the idea is that we want to be as close as possible for it to be reliable. And as we can see, it had like real close performance, especially in the combinations. And the cool thing about the combined cases is that, okay, perhaps you don't need to have like a huge data set, but you found like a little data set and you can combine it with something like we are doing, and you can get to have really nice results in segmentation classification. um, what is our future work in the simulator? Because I will show you all the things that we have done and what are the things that we're going to do in the future. Well, me personally, I want to try to see if I can simulate a UAV swarm to actually do a little more live test of the network that I showed you earlier, that was for multiple UAVs, for multiple flying robots. And the other thing that we need to is that we need to add more plants. We have been studying every now and then, taking interest in kiwi and vineyards, and we also have taken interest a little bit in virtual reality simulation, because we want to be able to see if we can offer some kind of training to the agriculture people that maybe not that tech savvy and they want to learn this stuff. I want to make it as easy and nice as possible as we can. And also the other nice thing that we could do with virtual reality is that in some case you can simulate yourself in the field and you can manage your field without actually being there. there are many things again, and you can control the robots through that. So there are really interesting research trends in all these directions. These are the things that we as a group have been interested in. So if any of you guys, the whole objective of this thing is to perhaps inspire you to take some interest in this kind of things. If this is your thing. So if by any chance any of these things that I have mentioned is of interest to you, these are some things that we're planning for the future in case you want to hop along and help us and do these awesome things, and make sure that you have the best simulation tools so we can stay away from the sun. Okay, I think that's everything, and this is my information. This is I'm here sharing also the data set with the simulator. I have to do a disclaimer, it's extremely messy at the moment, but I made it available because I have a conference coming on, and I have a publication where I made this work available, and I wanted to make sure that the dataset was available. So I'm making the dataset available through this GitHub repository, which I'll also have the simulator there in case anyone of you wanna take a peek. Like, it's a fun thing. You have it's a video game engine. You can have fun, throwing cubes there and see how it works. And then, if you get interested enough, you can download the thing and see how it looks like. And if you're interested, well, here we are with the open arms. Any questions?
There is one question, which is how much time did it take to create all this realistic environment, and how many different environments were created?
Well, the realistic environments, they took, well, it depends, because if you want to do it absolutely from scratch, it could take you quite some time, a couple of months, if you need to get all the data absolutely from scratch. But let's put it from some other perspective. Let's assume that you already have the textures, you already have the models, and you have already everything, and you also are sure of what you want to do, because this is one of the things that sometimes we say we want to do this, but then we build the environment, and we are not sure, like, okay, this is not, when it's ready, it's like, okay, this is not exactly what we wanted, and we need to do changes and other things. But try to put in some context, and the process of creating a script to the procedural field, like if you already have the models, it could take you like a couple of weeks, like 1 week or 2 weeks. It depends on how pro you are using this software. It also depends on your skill. And so to put it, if you're me and you're super pro and you need to create a field with, like, for example, I want a sunflower field, but I wanted with these certain conditions that are slightly different for yours, like it could take me like 1 week almost. But if you need, like, okay, we're not gonna do this absolutely new plant, and we need to create new shaders, and we need to do all these things, it could take you a couple of months. And that was one of the questions, like how much does it take? What was the other question, sorry? Because I think it was two questions one. Roberto? How many environments? Okay. In total, I could say 3, because we have the sunflower and we have the sugar beets, and everything we have done, it has been around making sure those things work, our experiments, because when the field is there, we're just tweaking it until it gives us the results that we want. So we don't have that many fields yet. It's just like 2 or 3, because I think we have a third plant, but I don't remember which one was. So that's about it. So that's precisely the idea. And if you want to create more field, we are interested in creating more fields, in creating the kiwi and the banyan, so that numbers that they are asking gets higher. But at the moment, we have little environments, but they are extremely flexible, so we can play around with them. So it's like having 100 in one. I don't know if that's answers the question.
So that's it. We don't have more questions, and actually this also closes our seminar course. So thank you again, Daniele, Mulam, and Carlos for presenting here today, and thank you to all of you guys who attended this course. Hopefully this has been an enjoyable experience despite the coronavirus issue. And yeah, good luck for the remaining parts of your studies. And yeah, so I'm closing the streaming now. Okay, see you, bye bye.